I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this video, we are going to discuss on the Niquist criteria and the Niquist plot. In this video, we will cover the topics of the frequency response, the Niquist stability criteria, the encircled and enclosed, the number of encirclement, the principle of argument, and rules to draw the Niquist plot and the Niquist contour. First is the frequency response. Now, the frequency response of a system is the response for sinusoidal input signals of various frequencies of the system. So, sinusoidal input means it is mathematically represented as A sin omega t, where this A represents the amplitude and omega represents the frequency of oscillation. And we know if the sinusoidal input is expressed as Rt equal to A sin omega t, then if we consider the Laplace transform, then it becomes A omega by A square plus omega square. Now the frequency response has some advantages. Firstly, the design parameter adjustment of closed loop system can be carried out easily in the frequency domain, as well as the effect of noise disturbances can be visualized very easily in case of frequency response rather than the time response. Also, it can be used to the higher order systems, whereas the time response becomes very much difficult to calculate in the higher order systems. So, in 1932, the frequency domain stability criteria was developed by the Niquist, and it remains a fundamental approach to the investigation of stability of linear control system. It is a graphical technique for determining the stability of the dynamic system. Now, the Niquist plots, which is actually a frequency response plot used in control engineering and signal processing. So, it becomes more commonly useful to assess the stability of a system with feedback. In Cartesian coordinates, the real part of the transfer function is plotted on the x-axis and the imaginary part is plotted on the y-axis. The frequency is swept as a parameter and resulting in a plot based on frequency. The Niquist plot can be described using the polar coordinates, where the gain of the transfer function is the radial coordinate and the phase of the transfer function is corresponding angular coordinate. Now, the stability analysis of a feedback control system is based on identifying the root locations. Root locations are actually the pole locations. So, it is based on the identifying of the location of the roots or poles of the characteristic equation. Now, the stability analysis, the system will be stable if all the roots of the characteristic equation lies on the left half side of the S-plane, and the relative stability of a system can be determined by the frequency response such as the Niquist. Now, what is the difference between the relative stability and the absolute stability? So, if a system returns to its equilibrium state after the inputs given to the system are removed, then that type of stability is known as the absolute stability. And the relative stability is the measure of how fast the transient dies out in a system. The relative stability is related to the settling time. A system with the poles away from the left half of the imaginary axis is considered to be relatively more stable when it is compared with a system having poles close to the imaginary axis. So the Niquist criteria is actually based on the complex analysis which is known as the Cauchy's principle of argument, and it is widely used in electronics and control systems as well as in the different fields for designing and analyzing the systems with the feedback. But it is still restricted to the linear time invariant systems, though it is the most general stability test. Now, in Niquist plot, the continuation of the polar plot to find out the stability of the closed loop system, and here we will vary the omega from minus infinity to infinity. That means Niquist plots are used to draw the complete frequency response of the open loop transfer function. So next, what is the encircled and enclosed, which is very much important in the Niquist. So if a point is found inside a closed path in a complex plane, then it is called the encircled. So if we consider this picture, so we can see that the point A, it is enclosed within this contour tau. So we can say that the point A is actually encircled by the closed path, whereas point B is out the side of this path tau. So the point B is not encircled by the given closed path. Next is the enclosed. So a point or a region is said to be enclosed by a closed path if it is encircled in counterclockwise direction or the point lies in the left of the counter traverse in the prescribed direction. So here we can see that this is a contour and point A is located within this contour or to the left of this contour in the counterclockwise direction. So we can say here the point A is enclosed within the contour, whereas in this diagram the contour is rotating in the clockwise direction, and when it is in clockwise direction, then we can say that the point B is located in the left hand side, whereas the point A is located in the right hand side. So here the point B is considered to be enclosed within this contour, whereas the point A is not enclosed within this contour. So after checking a point which is enclosed within the contour or not, then we need to find out the number of encirclement. So let us consider this is a contour and this point is the origin point, whereas the x-axis represents the real axis and y-axis represents the imaginary axis. So first we need to draw a line from origin until all the encirclements cut through the line. So we have drawn this line. Now we are considering that in clockwise direction the number of encirclement is positive. So after drawing this line from the origin, so all the encirclements has been cut through this line and the number of intersection is 2. So we are considering that number of encirclement, that is plus 2, because it is in the clockwise direction. So when the clockwise direction n is considered as a positive, then the z is actually the number of zeros of the characteristic equation, and this z is the summation of this n and p, where the n represents the number of encirclement which is considered to be positive in the clockwise direction, and in anti-clockwise direction n is negative, and P is the number of open loop poles of the system. So first we need to identify whether a point is enclosed to the contour or not, and after it is enclosed to the contour, we need to find out the number of encirclement of the point. And the next one is the principle of argument, that is the Cauchy's principle of argument. Here we are considering that Qs is a single valued function, or delta S which is a single valued function, and single valued function means for each point in S plane there exists only one point in the corresponding delta S plane which is a plot of imaginary value of delta S on the y-axis and the real part of delta S on x-axis. That is actually the mapping from S plane to delta S plane is 1 to 1 or many to many, but not 1 to many. So when we are mapping from S plane to delta S plane, will map one point to another point or many points to many other points, but not from one point to many other points. So this is known as a single valued function. So now if we consider a single valued function delta S that has finite number of poles and zeros in the S plane, and C is a arbitrary closed path or contour is chosen in the S plane, so that the path does not go through any one of these poles and zeros in the S plane. And the corresponding C delta locus mapped in the delta S plane will encircle the origin as many times as the difference between the number of poles and zeros of the delta S that are encircled by the S plane locus shares. So the principle of argument represents the number of encirclement n, that is equal to number of zeros. Z is actually number of zeros encircled by the S plane locus C delta in the S plane, and P is the number of poles of the delta S encircled by the S plane locus C delta in the S plane. So n represents the number of encirclements of the origin made by the delta S plane locus C delta, and that is equal to Z minus P. So from this principle of argument, there will be three cases. So first consider the case 1. So first, if we consider that the n, that is the number of encirclement of origin, is greater than 0. So if n is greater than 0 in this relation, then Z will be greater than the P. That means the S plane locus encircles more zeros than the poles of delta S in clockwise direction. And in this case, the delta plane locus will encircle the origin in the delta S plane n times in the same direction. Now another case that will be happen when n is equal to 0. So when n is equal to 0, that means Z is equal to P. So when Z is equal to P, that means the delta S plane locus will not encircle the origin in the delta S plane. And another case can be possible, that is n is less than 0. Now when n is less than 0, then Z will be less than P, and the S plane locus encircles less zeros than the poles of delta S in the prescribed direction, that is the counterclockwise direction. Now in this case, the delta S plane locus will encircle the origin in the delta S plane n times in the counterclockwise direction. we need to find out the rules to draw the Niquist plot. So, for a given problem, open loop system will be given, and from the open loop system, first we need to find out whether the number of roots at origin or is there any number of roots not in the origin. Because as per the selection, we need to find out which type of Niquist contour will be chosen by us. So, we will discuss on that point later. So, first check the steps. So, first we need to find out the number of poles of GSHS of the j omega axis including the origin or not. Next, we need to find out the proper Niquist contour. That means either if the system has the pole at the origin, then we need to select one type of contour, and if the system does not have any pole at origin, then we will select another type of the Niquist contour. But all the cases, the Niquist contour will include the entire right half of the S-plane by drawing a semicircle of radius r, whereas the r will tend to infinite. Next, we need to identify the various segments of the contour with reference to the Niquist path. So, after choosing the Niquist contour, we need to map each segment by segment of the Niquist contour by substituting the equation for the respective segment in the mapping function. Basically, for each section, we need to draw the polar plot of the respective segment. So, if a Niquist contour has 4 segments, then we need to draw segment-wise polar plot of 4 different segments, and then we will march the whole plot. And after that mapping of the segments, we will found that it will be the mapping will be the mirror image of the respective path of positive imaginary axis and negative imaginary axis. Next, the semicircular path which covers the entire right hand side of the S-plane generally maps into a point in the GSHS plane. So, after mapping all the different segments, we need to merge them and interconnect all the mapping of different segments to find out the required Niquist diagram. So, after that, we need to find out whether the transfer function characteristic equation is 1 plus GSHS equal to 0. So, if 1 plus GSHS is equal to 0, that means GSHS is equal to minus 1. Now, this minus 1 point, if we draw the x-axis and imaginary axis, then minus 1 point is actually located on the minus 180 degree line, and the imaginary part of this point is 0. So, this minus 1 J0 point, or actually the minus 1 point, is known as the critical point of the characteristic equation or the Niquist plot. Now, we have to find out the number of encirclement about the minus 1 J0 point and then decide the stability by using the n is equal to z minus p, or z is equal to n plus p. So, if we find out that n value, that there again 3 cases are coming. So, first, when n is equal to 0, that means there is no encirclement. So, when n is equal to 0, then z is equal to p, and that is p must be 0 if n equal to 0 to the system to be stable. So, for the case 2, when n is greater than 0, that means the clockwise encirclement. So, p becomes 0 and z not is equal to 0 and z greater than p. So, for both the cases, z equal to 0 and z greater than p, for both the cases the system will be unstable. And for the third case, when n is less than 0, that means the counterclockwise encirclement, then if z is equal to 0 and p becomes not equal to 0 and p becomes greater than z, and in that cases, both cases, that p is not equal to 0 and p greater than z and z is equal to 0, the system will be stable. So these are the rules to draw the Niquist plot and finding out the stability from the Niquist plot. So next is the Niquist contour. In the rule 1, I have said that after getting the number of poles at origin, or if a system does not contain any pole at origin, then we need to choose the Niquist contour. So how to choose the Niquist contour? In Niquist contour, it will cover the entire right hand side of the imaginary axis. So when there is no pole at the origin, then we will consider this Niquist contour, which has actually 3 sections. So for the first section, it will from this side to this side. That means omega is varying from 0 to the infinite. So this one becomes the section 1. And for the section 2, we will consider the semicircular path which has the infinite radius. So in the section 1, we know that this is on the imaginary axis and the real part becomes 0. So here omega varies from 0 to infinite, and for the mapping of the section 1, we need to put s is equal to j omega as the real part becomes 0. Next, for the section 2 means this whole semicircular arc with infinite radius, and here omega varies from plus infinite to minus infinity, and this semicircular arc have the infinite radius, and here the theta varies from this is plus 90 degree to minus 90 degree. And for mapping of this section 2, we will consider that r e to the power j theta, where the r tends to infinite. And for the section 3, the last section, this is the section 3, here the omega is varying from minus infinity to 0, and it is the mirror image of the section 1. So for the system which does not contain any pole of the origin, then we will choose this type of Niquist contour which has 3 segments, and for the section 1, omega is varying from 0 to infinite. For the section 2, it is varying from omega is varying from plus infinite to minus infinity, and it is a semicircular arc of infinite radius where theta is varying from plus pi by 2 to minus pi by 2. And for the section 3, the omega is varying from minus infinity to 0, so it is the mirror image of section 1. Now, if the system have pole at origin, then we cannot select this type of Niquist contour. In that case, we need to consider this type of Niquist contour. Here the difference is here we are considering a small semicircular arc which does not contain this origin. So here the section 1 is varying from 0 plus to plus infinity, and omega is varying from 0 plus to infinity, whereas the section 2 remains same as the previous contour. That means section 2 omega is varying from plus infinity to minus infinity with a semicircular arc of infinite radius, and for mapping we will put s is equal limit r tends to infinite r e to the power j theta, and theta is varying from plus pi by 2 to minus pi by 2. and section 3, that is omega is varying from minus infinity to 0 minus, and that is again the mirror image of the section 1. And for the last section, that is the fourth section, and here we will consider that the radius is very small, that is r tends to 0, and the remaining will be same, r e to the power j theta or s e to the power j theta, where s is varying very small, that is limit tends to 0, which will actually the semicircular arc of very small 0 plus radius. So these two types of contour will be chosen for complete the Niquist diagram, and then after choosing this Niquist contour for each section we will consider the polar plot, and after completing the drawing of polar plot of each section we will merge the whole thing into to get a complete Niquist plot. So how to find out the Niquist plot and how to find out the stability from the given problem, we will discuss that on our next video. These are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.